Hello everyone. Welcome to our another lecture on material science. This one will be dealing with principles of material selection, mostly looking from sustainable material selection. So by the end of this class, your expectation is to understand the three principles of sustainable material selection, which I introduce as reduce, extend, and close. Where reduce means reducing the resources, extend is extending the lifetime of the product, and close is the closing the loop by reusing or by other mechanisms. So sustainability in material selection can be summarized with three buffs, as I mentioned earlier. Um, One is reduce resource use. So idea here is to use less mass to achieve the same function. Some engineering things that we can do for reducing the resource use is lightweighting the product, topology optimization, and manufacturing the products in a near net shape using the near net shape manufacturing, which minimizes the waste. The second principle is extending the product life. So here our focus is on choosing materials that resist corrosion, fatigue, and wear to reduce the replacement frequency. And final principle is closing the loop, where we design the products for reuse, remanufacturing, and recycling. For example, we favor mechanical fasteners over adhesives and ensure components are easy to separate. These three principles, they reinforce each other. So for example, reducing mass is only sustainable if durability and repeatability remain high. Let's look into the case study. This is the Tesla's Model 3 body frame. So Tesla Model 3 uses high recycled aluminum for the car body to cut weight and corrosion. It also integrates bio-based polymers in interior components to reduce reliance on petroleum-based plastics. While the production energy of aluminum is almost 10 times higher than steels, the use of recycled aluminum actually reduces the production energy, and it also reduces the mass, and that lowers the operational energy consumption, and it results in a net positive life cycle balance. So next, we'll look into each of those three principles and look into the key strategies to achieve those principles. The first one um, is reducing the resource use. So here the goal is to minimize resource extraction and material volume while maintaining performance. While maintaining performance. So the key strategies to reduce resource use is one is lightweighting. So we reduce the mass using high specific strength materials. The second one is topology optimization. So we remove unnecessary material from the design, and we do near net shape manufacturing, which minimizes the machining waste. And finally, the fourth strategy is to use energy efficient processing. So usually we try to get fewer steps to achieve the same product. So fewer steps means less embodied energy in each step. So let's break down these key strategies um, one after another for the first principle of the material selection, which is reduce resource use. So the first key strategy is lightweighting. So here we are reducing the mass using high specific strength materials. So we select materials with high strength to weight or stiffness to weight ratios so that the load can be supported with less mass. These are materials which have high values of sigma y by rho or E by rho, which is where the sigma y is the yield strength and the rho is the density, or Young's modulus is represented by E and the density. So some examples of lightweighting include application in aerospace, where we substitute carbon fiber in polymer or titanium aluminum vanadium alloy for aluminum in aircraft wing for the fuselage frames. And this helps reduce the weight by 20 to 40%, which translates into consumption of almost 15 to 20% lower fuel. Another example is in automotive, where using advanced high-strength steels and aluminum 6000 series alloys for body panels and glass panels, instead of mild steel, we can achieve the same strength at around 30% lower mass. One easy idea to look into the um, the width strength versus density is looking into the SP chart. So an SP chart of the strength versus density plot um, gives the strength of material on y-axis and the density on the x-axis with different material class, such as metals, composites, clustering in distinct regions. So looking into these, we can actually initially think about what kind of material we want to utilize for a given product depending on the strength needed of that product and what is the density we want to apply to that product. And usually the materials, they cluster around a given class. So metals cluster on higher end of both density and strength, while foams lower end of both density and forms. The second strategy to reduce resource use is through topology optimization, where we remove the unnecessary material. The idea here is that topology optimization uses computational tools such as ANSYS FEA modeling tools to determine the most efficient geometry that carries load while removing excess mass. Think of it as a digital evaluation where the algorithm keeps the material where stress is high and it erodes everywhere else. So if we watch this video,
the world of product design is a constant race. Let's examine how topology optimization, a widely used simulation-driven design technology, can give manufacturers a head start. Imagine a simple beam that needs to carry a single load. Engineers can typically draw upon experience to propose a workable solution. But when faced with a complex part packaged into a tight space that needs to carry multiple loads, they could use a helping hand. Rather than validating an existing design, topology optimization uses physics to enhance human creativity by proposing forms that can be easily evolved into a finished product. It enables rapid design exploration and improved development productivity, all while flagging opportunities for part consolidation. Engineers can apply manufacturing constraints at the beginning stages of design, including material, extrusion, symmetry, draw direction, cavity avoidance, and overhead angle. They can define where structure can and cannot be, and apply the expected loads that the part will see in use. Topology optimization takes it from there, generating optimal, manufacturable structures that meet performance objectives with minimum mass or maximum stiffness.
So yeah, I think that video was helpful to give an idea of why topology optimization helps reduce the resource use.
The world of
So let's move to the next slide. So some of the examples here are the machine tool frames, where the generative design creates hollow ribbed structure in cast iron or polymer concrete, maintaining rigidity with less volume. Another example is in robotics, where lightweight lattice joints are printed in aluminum, silicon, magnesium, aluminum alloy, and they allow smaller actuators, which lower the total energy system. So this figure shows the original design. If you use FEA, it shows the areas of stress concentration, and we start doing topology optimization, and we will get our final optimized design with the reduced mass, and then we can do the final validation using FEA results before we actually start manufacturing the product. So moving from the original design to the topology optimized design, we can reduce a lot of material during the processing, manufacturing of the component. So the third strategy to reduce the resource use is near net step manufacturing, which minimizes the machining waste. The idea here is to produce components as close as possible to the final dimensions, which reduce machining, scrap, and energy use. The main idea here is that each kilogram of chip waste especially from milling or other machining, represent not only the lost in material, but it also means there is a loss in embodied energy. So you are spending a lot of materials and a lot of energy to get some product. But then if you can substitute that with manufacturing techniques that actually make products that are almost near to the final production shape, then we can minimize the loss. So in this figure, we have two examples. One is we have a block of metal material, let's say maybe iron block or something that we get from raw material manufacturing. and then we actually want to get a 3D object is shown here, um, and this object, and then we do what is called as a traditional subtractive manufacturing, where we do a lot of operations such as drilling or machining. So we get the final object, but at the same time, we get a lot of material waste. And also because we are working from this material to cut out this section, we are also losing a lot of energy. So that is both material as well as energy resource loss. And if we have a power from that material, and if we actually use additive manufacturing, which is one of the near net step manufacturing techniques, we can actually get the final product with the minimum waste. In that case, we are reducing both the material use as well as the energy use. Some examples include, as shown here, is the one is the additive manufacturing or 3D printing. So laser powder bed fusion of titanium lattice structure for aerospace engineering gives an 80 to 90% material utilization versus 10% in the conventional machining techniques. The other technique is metal injection molding, where we can get the near net shape production of small steel components like gears or nozzles, eliminating the secondary operations. The fourth key strategy is to reduce the fourth key strategy to reduce the resource use is using the energy efficient processing. Basically, as I discussed earlier, if you can come up with fewer steps or processing techniques that require less embedded energy, you'll reduce the resource use. Each thermal or mechanical processing steps adds embodied energy, which is usually measured in megajoules per kilograms, and reducing steps using lower temperature routes or switching to a renewable energy source directly that lowers the footprint of the energy use. Those examples include recycling routes. So remelting recycled aluminum scrap only consumes around 5% of the energy required for the virgin production. Um, the other idea is hybrid manufacturing, where we combine both additive for geometry and machining for precision in one setup to avoid multiple heating cycles and handling steps, thereby reducing the energy consumption. So this graph shows the embodied energy for steel, aluminum, and copper uh, during the processing. So if you are using virgin steel versus recycled steel versus the typical industry consumption, you can see that for steel there is still a lot of um, change when moving from virgin to recycled steel. But especially for aluminum, you can see that the embodied energy is more than 63 kilowatt hour per kilogram for the virgin aluminum. But then if you switch that to recycled aluminum, you only have to spend around 5 kilowatt per kilograms of the aluminum. That is why a lot of time reducing using materials like that can help with reducing the energy during the production. So with that, the second principle of sustainable material selection is extending the product life. The goal here is to maximize the useful lifetime of a product or component to reduce the replacement frequency, waste, and cumulative embodied energy. There are a few key strategies that can be applied to extend the product life. One is making corrosion-resistant materials such as stainless steel coatings. Second one is fatigue and wear improvement using techniques such as surface hardening. Third key strategy is designing for maintenance. So it should allow for easy inspection and part replacement rather than doing the entire replacing the entire material. Modularity is similar in the sense that you make components that are modular, so it's easy to replace those modules and not the entire systems. So the first strategy, corrosion resistance. Here the idea is that the corrosion deteriorates the material through electrochemical reaction with their environment, leading to thinning, cracking, or structural failure. And improving corrosion resistance thus prevents premature replacement and reduces both the maintenance cost and the embodied energy. Corrosion is governed by thermodynamics, which is the tendency to oxidize, and kinetics and the reaction rate. And engineers counter corrosion through multiple different techniques such as alloying. So adding chromium, nickel, molybdenum to form a passive oxide film, such as in stainless steel, is a strategy to increase the corrosion resistance. Surface coating, applying barriers, paints, polymer films, anodizing, and galvanizing are some of the surface coating techniques that can help enhance the corrosion resistance of material. Cathodic protection, so we apply sacrificial anodes or impressed currents to protect the surface of the material. Um, So some examples include stainless steel, especially ANSI 304, 316 for marine structures, which forms a self-healing chromium oxide passive film. Also, another example is galvanized steel in automotive chassis. So we have zinc coating that corrodes preferentially protects the steel underneath the zinc coating. The second strategy for extending the product life is fatigue and wear improvement. So the fatigue and wear cause microscopic crack initiation and propagation under cyclic loading or friction. Surface treatments enhance mechanical durability by modifying those microstructure or the surface chemistry. So fatigue initiation usually begins at surface defects, and we can reduce with compressive residual stress or microhardening. Wear, which is caused by abrasion, adhesion, or erosion, can be reduced with harder or lubricated surfaces. There are a few techniques to increase the fatigue and wear improvement in the materials to extend the product life, such as carburizing or nitriding, where we introduce carbon or nitrogen into steel surface. For example, hard martensitic layer improves fatigue strength by 30 to 50%. The other idea is short pinning. So we bombard surface of material with small steel beads, which creates compressive stress layers, which delays crack growth in the material. Similarly, other technique is laser surface melting, which refines the grains of the surface, seals any micro cracks, and it increases wear resistance. The other technique of wear and fatigue improvement is thermal spray coating, where we apply hard ceramic such as aluminum oxide on turbine blades or shafts. And another technique is physical vapor deposition, where titanium nitride coatings are applied on the cutting tools that increases the lifespan of cutting tools by almost 3 to 5 times. So some examples include gear teeth in automotive transmissions, which are usually nitrided or carburized for extended service. Um, and another example is diesel injector components, which are coated with diamond-like carbon for wear resistance. The third key strategy for extending the product life, which is the second principle of sustainable material selection, is design for maintenance, which basically means we should design materials that allow easy inspection and part replacement. That is because even durable materials need keep up, and designing for easy inspection, cleaning, and repair ensures minor failures and don't force total system replacement. The engineering focus here is to incorporate accessible joints, standardized fasteners, and replaceable liners or bearings. And we also use predictive maintenance sensors to detect fatigue or corrosion early in their stage. These are some examples. So industrial pumps usually have quick release seals, which reduce the downtime and prevent early scrapping. In more machine tools, we can use replaceable carbide inserts instead of resharpening the entire cluster. So in this machine tool, we can just use this section, which after wear can be replaced rather than having to replace the entire section. So these are some of these key strategies. The fourth key strategy for extending the product life is modularity. Um, that way you can just replace modules and not the whole systems. The whole idea here is divide a product into independent functional modules to so the upgrades or repairs that can occur without discarding the entire assembly. From mechanical perspective, modularity requires standardized interfaces, bolts, flanges, connectors, and independent load paths, allowing a one or obsolete part to be replaced while preserving the rest of the system. One example is Fairphone smartphone. So user can replace the screen, camera, battery, etc. That extends the lifespan of the phone by 2 to 3 times the normal phone that is built as a system. So in even electric vehicles, a lot of people use modular battery packs, so that then you can just replace the defective cells individually rather than to having to replace the entire module. So, so these are the key strategies to extend the product life. Um, in industrial robots, we can use standardized actuators, which can allow quick swap without redesign. Similarly, in jet engines, we design modular replaceable units are used for compressor and combustors. Similarly, in the wind turbines, the blade and gearbox modules allow partial overhaul instead of full teardown. That is the key strategies for the extending the product life. So the third principle of material selection is closing the loop. The goal here is to design materials, products, and systems so that they can re-enter the production cycle after use through reuse, remanufacture, or recycling rather than ending as a waste. Core idea here, we move from linear systems such as take raw material, make something, and dispose it to a circular economy concept, which is we make something, we use that, we try to recover as much as possible from that product or service, and then we try to remake from that. There are a few key strategies to close the loop. One is designed for disassembly, so using bolts, clips, and reversible joints that can allow for disassembly of the materials. Material leveling is really important technique because it simplifies sorting during the recycling. Um, the other strategy is single material design where possible, which helps with avoiding inseparable composites, and using recycled feedstock when performance allows. So those are the four key strategies to closing the loop. So let's discuss those key strategies one after another. The first strategy is design for disassembly. In this case, the products should be easy to take apart, so the individual materials or the components can be reused, repaired, or recycled without destruction. The engineering logic here is to avoid permanent joining, such as wales or adhesives between dissimilar materials. And we use mechanical fasteners such as bolts, screws, snap fits that enable separation. We use standardized interfaces for easier replacement. Um, we apply reversible adhesives or low melting point soldiers where joints are necessary. Some examples of design for disassembly is wind turbine blades, where modular bolts at the hub interface make the hubs reusable. Um, in appliances, there are most of the times the panel circuit boards they are screw mounted instead of glue seams, and that way the recyclers can remove those electric boards separately before recycling the home appliances. The second key strategy is to enable material handling by simply simplifying sorting during the recycling. So the idea here is to clearly labeling of materials, which enables efficient separation and accurate downstream processing. The engineering logic here is that different polymers, alloys, or composites melt and react differently, and mixing incompatible materials can ruin the entire recycling batches. So the labels that they will ensure each material re-enters the correct loop. Some of the examples of material labeling strategies include polymer components, such as they have embodied codes such as PP, PET, or ISO 11469, that enable automated sorting by optical scanners. In aluminum alloy, their laser is temper codes to prevent cross-contamination and remelting. In electronic OS, they have barcoded or RFID tagged circuit boards that track material composition for closed-loop electronic recycling. Another key strategy to close the loop is single material design where possible, which avoids the inseparable composites. The idea here is whenever feasible, design products from one primary material family or materials that can be thermally or mechanically separated at the end of their life. Um, Composite and hybrid structures often have unmatched interfaces. So carbon fiber plus epoxy, metal polymer in laminates, they are nearly impossible to separate. Using a single material or compatible ones preserves recycling efficiency. Example, all aluminum laptop chassis instead of plastic metal hybrids are 100% recyclable. Monomaterial PET bottles and PET caps, where usually plastic bottles and caps are made from different material. If you utilize same material for bottles and caps, then it is easy to recycle into high-grade feedstock. Um, Another example is steel-only fasteners in bicycle, so that avoids the galvanic corrosion and simplifies the melting if we are going to reuse those fasteners from bicycles. The final key strategy to close the loop is using the recycled feedstock when performance allows. So the idea here is to replace the virgin raw materials with recycled or secondary feedstock where mechanical or aesthetic properties meet the design requirements. The recycled metals retain nearly all original mechanical properties like atomic level degradation. Um, Polymers, however, can lose chain length, and that is why they require stabilizer or blending with virgin resins. Ceramics and composites often downcycle as they aggregate as aggregates or fillers. Some examples of using recycled feedstock is an aluminum beverage cans. So more than 70% is made from recycled aluminum, and remolding only uses around 5% of the virgin smelting energy. So we are recycling and we are reducing the energy consumption with this strategy too. Recycled steel scrap in electric arc furnace steel making reduces the carbon dioxide emission by around 60%. So um, these are the key strategies. I hope this helped you understand the key principles of sustainable material selection, and that is all for the lecture today. Thank you.